So let us actually then just let us continue with the cuts thing first, and in the end we can do that minimum spanning trees thing. Okay. So we were looking at what? We were looking at cut vertices, right? We were looking at cut vertices, and so can anybody recall the definition of a cut vertex? How did we define this? No, that is a no cut vertex, right? So I think what you've said is the opposite. So a cut vertex, right? So a cut vertex would be, let's see, if we take a small graph, just a very simple one, this, then this vertex, this blue vertex is a cut vertex because its removal cuts the graph, basically you could say, right? Its removal disconnects the graph. So this is a simple definition of cut vertex. Okay, so a vertex. So let me just say cut vertex. Cut vertices can create a misconception. So one has to be careful. A cut vertex. Now cut vertex is just a vertex. Sorry. Vertex whose removal. So obviously when we say whose removal, we mean the removal of the edges also, like automatically they get removed, right? Whose removal disconnects the graph. This is the definition we are taking. Then the definition of a no cut vertex is we don't even need to define it, right? No cut vertex. This is just a vertex that is not a cut vertex. This concept. Why are we looking at these concepts? Because see, in a graph, there are many vertices, right? There are so many different vertices, but there are some vertices which are special, right? No cut vertices are special in some sense, right? Because they are kind of, so they are kind of the leaves of a graph. Now this I'm putting in quotes because it's not actually leaf, but it's kind of, like something that are in the end of a graph, like on the boundary of a graph, right? Leaves of a graph or boundary. So these are important special vertices of a graph, which you can use to do reasoning. We will see this concept. Actually, we did do induction on leaves to prove some other things earlier, right? So yeah. Okay. So what was the result we proved about existence of no cut vertices? We proved that every, let's say connected, okay, for the time being, otherwise there will be problem in the definitions. But conceptually, every graph has a cut vertex, no, has a no cut vertex, but every connected graph has at least how much? How many? How many no cut vertices? So no cut vertices are like these, these. Those whose removal does not cut the graph. That's right. It will have at least two. Now all this we have proved. You can again try to think why. But even you can see in this graph, there will be at least two. So no matter how complicated the graph is, it could be a very rich graph, a lot of edges, so on, but it will have at least two no cut vertices. Well, the richer the graph is, it's easier, right? There will be more and more no cut vertices, but it will have at least two. Now again, a very simple question. Example of a graph with exact, and I'm just doing all this just to get intuition for things, okay? With exactly two no cut vertices. Sorry, what is happening? Example, exactly 2. Line of points. You mean line of points means I'll just join them by this, like this. Okay, is this it, or do you want something else, something more? Just randomly outside? No, but then it will not be connected. Middle ones meaning? No, this is it. This is an example, right? This has 2 vertices which are no cut. Right, this itself is an example. So maybe I should just be again careful here. I'll just say 1, 2, 3, 4. I'll say like this. 1 is no cut and 4 is no cut. Now there is no such thing as saying 1 and 4, like 1 comma 4 is a no cut. No. No cut vertices is always one at a time. Something is no cut is only one vertex at a time. Okay. So when you remove 1, so this is the graph G. 4 is no cut. Okay. From G, so G minus 1 is connected. Okay. G minus 4 is connected. That's all. See, G minus 1 comma 4 is also connected, but that is not our interest. Okay, but we are not at all interested in this. Okay, so that will be a misconception. Okay, then you will end up saying the 3 is also no cut. Right, 1, 3, 4. You can say, but no, we're just saying one at a time. Okay, whose removal from the original graph? Whose removal from the original graph? I mean, that is understood here, from the original graph. Okay, so these are simple. So paths are examples. Are there any other examples? Any other examples? Now this can be framed combinatorially also. You have some because some set of roads and cities in roads, and there are 2 cities whose removal is not disconnecting the network, and there are only 2 of them like that. Then prove that it is something, or give example. So I'm just framing it abstractly, not abstractly, but just mathematically, I should say. Are there any other examples? This is the key question. Use your intuition. If you have some other graph, so remember, it should be a connected graph. Can you think of some other connected graph which has only 2 vertices which are no cut? And there is no other. So you're saying it should have only two vertices of degree 1. Okay. Certainly cycle will not be there, but yeah, but cycle obviously, cycle will not be working here because cycle everything is a no cut. But yeah, this property we can write. Uh, it has exactly two vertices with degree 1. Can you give explanation, or can anybody give explanation? So he's saying that any such graph. Okay, so you were saying start with a cycle, then then but this will have many no cut vertices, right? No, no, no. Okay, let's see. So you're saying this like this first, but this has no. So there will be vertices which are cut vertices maybe, but that is not the point. Point is that how many vertices are there which are no cut? There are many. This is no cut. This is no cut. This is no cut. You see. So so again, I'm not saying that remove them together. No, I'm saying that you take any one of those pink vertices, when you remove them, the graph kind of remains connected, still remains connected, right? You can see. Even then you have, no, but then it's just a path. So there's not a new example. Okay. So Chandan, can you explain this, why it should have exactly two vertices of degree 1? Yes, right. So any vertex which is of degree 1 is a cut vertex. Is a no cut, sorry. So any, let me just write that, and I'm not explaining it, okay? I already, you should try to figure this out. Any vertex which is degree 1 is no cut. Means it doesn't remove, because you can intuitively understand if it is a degree 1, then it is here, and the rest of the graph is here, right? So removing this vertex is obviously not going to disconnect the graph, because this doesn't have responsibility of connecting anything else. So in some sense, I'm asking for examples of graphs which have exactly which have exactly two vertices of degree 1. But cycles do not work, right? Or if you want to modify them, but otherwise cycles do not work. In cycles, actually everything is a no-cut vertex. You remove any one of them, it doesn't disconnect, as you know. So you can see, the point is that you can try to now construct a graph in which there are only two vertices which have degree 1. But But the point is that there may be other vertices which have higher degree, but they can also be no cut. Right. So, okay, let's not get into all that complications. Let's think about this simply. And that can help us to get to the answer, but that just gets very, very logical. And just go with your intuition. Can we again use the idea? But that will only make it worse, right? Because there will be, then you'll get many no cut vertices. For paths is obviously possible. Okay. So yes, no. So so in this one, you have many no cut vertices. This is a no cut, this is a no cut, this is a no cut, this is a no cut. But in paths, that is not the case, right? In paths, only two vertices are no cut vertices. Yeah, let's try to understand this. So if you have this path, then is 3 a no cut vertex? No, it's if you remove it, it's just disconnected. Right? When we say something is a no cut or not, we're saying if we only remove that, then what happens? Don't think if I remove 3, 4, and 5, then no. Only removing 3, because removing 3, 4, and 5 actually changes the graph. Okay. So for paths there are exactly 2 no cut vertices, right? But here the situation is obviously different, right? Because here you can remove any of those pink vertices that are 1, any one of them, and it still remains connected. So the situation is very different. Okay. All right. Okay. So I think we are developing some intuition. Let's go on. Let's see. So can we again use the minimum spanning trees? Can we use the idea of minimum spanning trees? I don't know. You have to think. Because as we've seen, it has been very useful always in the past. Okay, let me ask maybe a slightly more specific question, I should say. Give example of a tree. Sorry. Give example of a tree with exactly. So now I am not asking for a general connected graph. But I'm asking for a tree. Okay. Give example of a tree with exactly 2 no-cut vertices. I mean, which is not a path. Path we already know. Anything anything more interesting if there is. I'll write it like this: two vertices which are no cut. Sorry. Trees we have seen a lot. So you think based on your intuition. So basically I'm asking tree with exactly how many leaves? Anyone wants to fill this? Like, this question is the same as how many leaves should your tree have if you wanted to have only two no-cut vertices? Two no-cut vertices. Only two. A tree. Absolutely, right? You just want the tree to have two leaves. So can you draw a tree which has only two leaves, which is not a path? No, right. So yeah, right. So this, but such a tree must be a path. Try to give a reason. Okay. Try to let's all think about this for a minute and try to give a reason. If we cannot, then this will be homework. But this is not so difficult, maybe, because now we have come down to a tree. Not come down. We are dealing with a simpler question. It's a tree. Okay. It does not have any cycles. You mean definition of a path? Okay. Define a path. Okay. No, so path is actually I've not defined a path. That's right. But okay, what do you think should be the definition of a path? No. That is because you can make many figures like that then, right? Come on, someone give me a definition of path. Make your definition. Make a see, because if you say a degree is not greater than 3, that's not a good definition because you can make many graphs which you would not like to call a path in which there will be such things. No vertex with degree greater than 3. Someone define a path, please. Use your common sense. So in the sense that you want this, I mean, you know how a path should be. I have to just define. So obviously, right, a path, yes. In terms of vertices and edges. A vertex, that's an interesting definition. Okay, that's an interesting definition. A vertex cannot have more than 2 children. Okay. Yes. No, this is not a correct definition. You are right. Because just if you remember the last class, we were doing binary trees. So there also it is like that. Yeah. So this definition, and I know something can be added to make it, but let's not go into that. Right. In fact, um, from what? Infinite. Why infinite? Finite. Yes, yeah, you're right. A finite sequence of edges, right? So the edges, so path is basically a graph in which the edges are v0, v1. Let's say this is an edge, and then v1, v2 is an edge, and let's say path of length 10 or something. v9, v10, these are the edges. These are the edges, and no more. Means, I mean, I've already said it, but just saying it, okay? These are the only edges. Okay, so path is basically a graph in which you can arrange the vertices. I mean, set theoretically, you can number the vertices like this, such that the only edges are v0 to v1, v1 to v2, v2 to v3, v2. These are the only edges. There are no other edges. Okay, so you have basically you have some vertices such that the edges are in a sequence. So it could be like this also. There is an edge from here to here. Then there is an edge from this one here. Then there is an edge from this one here. Then there is an edge from this one to here. Then from here to here. So you've got a sequence of edges that joining everything eventually and no more. Okay. So this is the definition of a path. Now it should be very simple to see, though proving it may be slightly irritating, that a tree cannot have more than, I mean, cannot have exactly 2 leaves, right? Unless if it's a path. Because, right? Because if, um, yeah, let's do it because I think no one has got it concretely till now. So let's do it. Let's make it more. Let's say V and W are leaves. Then what can you say about the tree? It's a tree. So let's say P and W are leaves and the only leaves. We want to prove that the tree is a path. So it's a tree. I don't want to draw any vertices, many edges at least. So I'm not drawing any edges, but let's see the other vertices. So let's say that this is a leaf, right? V is a leaf. Then what happens? It means that it has a parent. Okay. Can it have more than one parent? Yes, right. That's absolutely correct. I mean, obviously, sorry, I was. Okay. Now you see this vertex that we have found, this has a parent, this has a parent, and then so on. Where should you end up? To W, right? Does everybody see that? Because if you end up in some other place, end up, end mean end, then that also becomes a leaf. Is that right? If you end in some other place, then that also becomes a leaf. So you have to end at W. Now you may say you don't have to end at all. You may go back to somewhere, but you cannot because it doesn't have any cycles. This is not a proof, okay? I have a proof in mind, but I'm just saying the reason, kind of, okay? So it has to end at W. There is no other way. And this on this path, any of the intermediate points cannot have any more tentacles, right? Cannot have anything more coming out of them. Otherwise, that will end in some other place, right? If from here there is some edge, then this has to end in some place which is outside this path because you can't afford to have cycles. Not having cycles makes the reasoning simple. Do you guys see that? The fact that trees are an extremal quantity, yeah, they are the maximum minima, they are the minimum of some function, kind of, right? So it's a very easy to do reasoning there because there is no cycles. So this path has to end somewhere, but end somewhere means that will again be a degree one thing, it will again be a leaf, which which we cannot have. So it has to be a path. How would you say this rigorously? Please think. It's very simple. Some things you have to say, but now just take a minute and just see if you get the roughly you get the reasoning at least. Intuitively, it's okay. Like a tree, right? How can a tree only have two leaves? It will become a path only, but we are proving it. Okay. So would anyone want to explain again or in a different way, maybe better actually, that why a tree cannot have two leaves? Why a tree cannot have exactly two leaves? I mean, a proper tree, not a path. Path is also a tree, but so if a tree has only two leaves, then it's a path. Yeah, let's see. Someone should come forward and try. Mm-hmm. Yes. Yeah. Or it's like a sequence of edges joining two vertices and no extra edges. Same thing. Yeah. Yes, yes. That's yeah. So how would you say? Right. Yeah, and so yeah. Mm-hmm. Right. So why should it be a path? No, no, no. Path is the same thing is okay. But why should this be a path? You see the point, right? The path has that property is fine. We want to show that nothing else is like that, right? Yeah, we want to prove this is a path. Path has that property is a different. That's easy, right? Right. You see, yeah, right, right. We want to show this will become a path, right? We want to show that tree with exactly two leaves is a path. We want to show this is a path. Yeah, path has this property. Mm. So I gave a rough explanation. Mm. So V and W are leaves, right? V and W are leaves. V and W are the only leaves. Okay. Then you want to show that. So show that, and see, intuitively it's fine, but the point is you're not able to prove it. Show that T is a path. For those who are very good in induction, you can use induction. So there are two paths to proving this, right? You can use induction also, but let me not go by induction. Okay, let us just try to see it like this. So show that T is a path. Okay, see, you want to show that T is a path, but already there is a path from V to W. V and W are leaves in a tree. In a tree, between any 2 points, there is a path, right? So let P be the path, because we know there is one path between any 2 points in a tree. It's an optimal thing. Let P be the path between V and W. So again, what do I mean by path here? Just the sequence, as you can see, sequence of edges, right? This. So what do we want to show now? We want to show that the tree is this P. Do you guys agree? Right? So we want to show that P is P. There is no more things in the tree. No, T is already in the path. P is already in T, right? Right? The path is in T. Right. So if you add the path to T, it will not change anything. So it will not form a cycle. Right. The P is already in T. Isn't it? That's yeah. But you see, you want to show that this is the tree. If this is not the tree, then there is some other vertex. Just for sake of contradiction, right? Basically, that's our intuition, right? That if there is some other vertex outside this path, it is going to create a problem. Do you guys agree? Right? If there's some other vertex outside this path, it will create a problem. How will it create a problem? Well, it will create a problem because if there is some other z outside, then basically you can then then this z has to be connected with this path, right? There has to be a connection between these two things. So there will be some. So you have to write like this. There will be some vertex, I don't know, x in this path from where there will be a path to this z. Let's say like this. Is that right? Do you guys agree? Right? But then, I mean, I'm not saying this z is a leaf, but this new path that I've started, this green path that I've started. Okay, how did I start the green path? Very simple, right? Because I assume for the sake of contradiction that let's say there is a z outside, right? Outside of this. I know it's not possible, but we have to prove that. Assume that there is a Z outside. Now there has to be a path. That's what we are using, right? The tree has paths between any two things. But then this path has to end. I mean, this green path has to end. A path cannot go on forever. And the place where it ends, because it cannot form a cycle, right? So it has to end. The place where it ends, now I have to write this new path where it ends, that will be a leaf. Is that right? Yeah. The path will end, right? Because you say, okay, Z, let's say you can say, okay, next vertex is Z1, next vertex is Z2, next vertex is Z3, but we don't have infinitely many vertices, right? It will end. And you cannot revisit a vertex. You cannot visit Z1 again and doing a cycle, right? So it was to end, and that has to be a this new leaf. That's a contradiction, right? Is this clear? Is this, because now I've said the proof clearly. Okay. You see how that, yeah. Is it clear to everyone? If it's not clear, you say, I'll try to explain this again. Just take your time, there's no rush. So is it okay with everyone that a tree with two, Mhm. Okay, right. So see, we want to show that tree, so now I'll write this statement very crisply because we understand the statement as, right? Tree with exactly, so initially we were asking this for connected graphs, but then we are asking for this for trees. Tree with exactly two no-cut vertices is a path. Yeah, let's also remove this picture, and let's also remove this. So intuitively, this is clear. Intuitively, we understand this, but we want to prove this. Okay, so let's say that there are two no-cut vertices, sorry, two no-cut vertices. Then I mean, basically leaves. Yeah, so let me write it like this. Tree with exactly two leaves, is a path. Yeah, this is good enough, right? We can just prove this. Because if it has two no-cut vertices, it should only have two leaves. Because every leaf is a no-cut vertex. And those are the only, but yeah. Tree with exactly two leaves is a path. So let's say that V and W are the leaves. So say V and W are the leaves. Now, what do we know about trees? We know that between any 2 points, there is a path, right? So let P be the path. Path is just what we intuitively understand. Yeah, just a sequence of edges. Let's say like this. So there is a path. Between V and W, sorry, in T. Okay. Now, what's the next thing we want to show? We want to show. Yes. Tree is the tree. Yeah. What do we want to show in the end? We want to show that this path itself is the whole tree, right? Yeah. So claim P itself is the whole tree. P is in the tree, we know, but P itself is the whole tree. So how do you show such a thing? You have to assume that there is something outside, right? So assume that some Z is not in the path. So there is some Z outside. That's a different color, Z. Now what? Now this Z must be connected with something from this path, right? Again, we are using the fact that a tree is a connected thing, right? Between any two things, there has to be a path, right? For example, from Z to W, there has to be a path, but that path cannot start from W like this because W is Z. So that path has to go like this, right? Okay. So basically, this path has to leave, I mean, this path from some vertex of this path, a new path must start, right? If there is something outside it. Yeah. So there must be a green path. So green path exists. So green path exists. Now, what kind of contradiction will we get now? We will end up showing that there are more leaves. Isn't that's the intuition, right? Because now already we have started a new thing, right? But this new thing must end somewhere. Yeah, this is the end. Yes, exactly, right? And we could see this coming, right? We knew that the moment you start a path, you start something outside, it will create a new leaf, right? Because every path creates a leaf in the end, right? Is that right? Yeah. Every path you start, you keep going along that, it will create a leaf in the end. There is no other way, right? Why should it create a leaf? Why should there be an end? Someone asks, right? It's because there is no cycle, right? If so, you have to write that, right? If there is no end, then you will get a cycle, but you don't have cycles. So you see, yeah. So the tree is the best place to do reasoning, right? And just imagine, right? This kind of reasoning you cannot do in an arbitrary graph, in an arbitrary connected graph. Because an arbitrary connected graph, you will get paths very good, but you will get cycles also. So in an arbitrary graph, you cannot say something like this. There also you have to do some reasoning. I'll take a maximal path and so on, so on. Okay, but in trees, you don't have to do such reasoning. Trees are a wonderful place. And the things you prove for trees, well, there is no theorem like this that if you prove it for trees, it will be true for connected graphs. Obviously, that's false. But I mean, 30% of the times at least it happens. There's something you want to prove for connected graphs. What tree ke liye you can prove, it will be good enough. Especially if it's a property like if it's a property like it's a property which only gets better with more edges. Right. I mean, if you want to prove a theorem or a property which gets better if you introduce more edges and more edges. Okay. Which obviously a property or a theorem that remains true if you prove if you add more edges. Right. Then such a thing, if you can prove it for tree, then it's good enough. Right. So this is like a meta point. Okay. So if if a property or theorem, but there are many things like this, right, remains true if you add more edges, right, then it is enough to prove it for trees. It is enough because you prove it for trees and then you add more edges in any connect, because any connected graph is gotten by starting from a tree and adding edges, right? We know that, right? Because from any connected graph, you can remove edges and you can get a tree, right? Yes. It is. So you just prove it for some spanning tree inside the graph, and then it will be true for that graph also. Enough to prove it for MST of the graph. So you want to prove some theorem for a graph, but that theorem is like, a theorem is something like which only gets better if you add more edges. You know, like any connected graph has at least n minus 1 edges. That's a trivial statement because a tree has at least n minus 1 edges, right? And we have, this is the trivial example, obviously. Okay, but the thing about trees is that reasoning becomes very easy because they have this uniqueness that there is exactly one path between any 2 points, or you have no cycles. Okay, this is why always in mathematics, whenever we have a family of objects, like a family of connected graphs, we'll try to look at the minimum member in that family, like a tree here. Okay, we'll try to look at its extremal member, because extremal member means that वहाँ पे you have more properties and you can prove it for that, then it will be true for all. Extremal principle is sort of based on this mysterious idea. Okay. Okay. So now what have we proved? Hmm? Yes, yes, no. So suppose there is a, suppose there is a family of objects. Let's say connected graphs. Okay. Connect family of objects and they are all, see, the points are connected graphs. Now you want to show something like, there is a connected graph in which this will happen, in which no edges will overlap or something. Something you want to prove. So you want to show that there is a connected graph which has where this is true. Okay, then you will say, okay, take a tree. Okay, consider a connected graph which is a tree. Then it becomes easier to prove it for a tree. So you pick an extremal member from this family and you show that it works. Okay, now it might, yeah, then it will work for all. Okay, but sometimes we just want to maybe find a member for which it works, and that member for which it works will be a special member. Okay, because at least because reasoning it for that special member, that special member has that property, will be easier, right? Because the special member has more properties, so it becomes easier to prove things about it. Yeah, it's a fact that it becomes easier to prove things about it. Okay, so yeah, I mean, other things, other members may also have that property, but it becomes easier to prove it for that special member. So we say, okay, you pick that configuration in which some of the distances is minimum, and there it will be true. It might be true for others also, but it becomes easier to prove it for that because you have assumed more things. Okay, so it's yeah. These are some, we'll see, as you will see these things on your own more when you do more maths. But yeah, okay. So what have we proved so far? That a tree with exactly 2 leaves has to be a path. But now you can feel that a graph, so this is, we have proved, this is done. A connected graph Okay, so this is basically means with two no-cut vertices is a path. A connected graph with two no-cut, any connected graph is a path. Now you can also intuitively feel this. How do we prove this? Hmm? Right. That's a little, you don't know, it can be very complicated, right? Cyclic system is what? It's a philosophical. Oh, so you're saying it should not have any cycles. That's an interesting, okay. So that's an interesting point. You're saying that it should not have any cycles. But you see, a graph can be very complicated. If what you're saying is true, then we are already done because we have proved it for trees. No, but the problem is that, see, if you have a connected, so if something is on a cycle, it doesn't mean that it is a no-cut vertex. That's a problem. It's a very complicated because an arbitrary connected graph, even the definition is very imprecise. There's no characterization. You see, I mean, this is on a cycle, right? But if I remove it, the graph gets disconnected. Now you may say, okay, but there are others, but I can do the same thing for them also. But then you may say, no, no, I can take this cycle. But you're right. But you this cannot say this in general that it should not have any cycles. I mean, in the end, what you're saying is correct because it will be a path only, so it will not have any cycles. But this is not straightforward. Okay, yeah. So maybe that's right. Maybe think about it. Yeah, that may be true. That you can try to prove that it doesn't have any cycles. Yeah. So then this is just a, we are not yet proved it. I mean, it is true, but we have to prove it. I shouldn't put a question mark, but yeah. Hmm, you take a sequence of vertices. No, but the point is that there may be other things outside the path, right? I mean, you have to, yeah, so you have to show that no vertices are repeated. Yeah, that's in the definition of a path. But the point is that you have to also show that there are no other vertices in the tree, in that graph. And that is how will you show that? That is the whole challenge. Because you can always, yeah, okay, but will there be a path running across them? That is a question mark, and that is not true. There will not be, right? I mean, there will won't be one path that runs across and visits everything. Will there be? No, no, that will not be the case. Yeah, right. You understand, right? You want one path that runs across every vertex. Now that is a difficult thing. That's so called a Hamiltonian path. That is not true. That doesn't always happen. I mean, so the word Hamiltonian is not at all important here, but that will obviously not happen. You can understand. Okay, let's think about this. Okay, cyclic system. Okay, should have it. Okay, yeah, at least 3 vertices. 3 things. Okay, 3 things will go out of it, but they may not be. No. That's the problem. As I was saying, it's not a tree. It could be very complicated. You can't imagine. Like literally, we cannot imagine what the possibilities are. I mean, it could. You don't know what will happen, right? It's not a tree. It could anything can happen. It could be like this, and then there could be another cycle coming out of this. Then there could be another cycle coming out of this. I don't know. And then you have to, yeah, it's difficult to say anything. How about we go to the minimum spanning tree, right? If the graph, so G has, okay, no one said this so far. I mean, it may not work, but at least you try it, right? G has exactly 2 no cut vertices, okay? So you look at the minimum, just the MST, right? The minimum spanning tree. Why minimum am I saying? Just spanning tree. Why minimum? There are no costs here. Look at the spanning tree of G. Okay, say T. I mean, just look at the underlying tree. Just look at the tree. Look at the skeleton of the connected graph. A skeleton. Now, T cannot have more than, can it have more than 2 no-cut vertices? No, right? If the original graph doesn't have more than 2 no-cut vertices, and then T cannot have, right? Because if in T, if you have, right, so that's again what I was saying earlier, a property which becomes better and better as you add more things. This is like that. I didn't give this example that time as when things will be done. I mean, I don't know, I had not planned any of it like this. In fact, I had planned a very bad proof. Okay, but luckily we have come to this proof, because when I'm repeating this philosophy to you guys about go to the minimum spanning tree and do the reasoning there, I'm learning things which I did not know before. Okay, so yeah, before I would have tried to prove this in a very bad way. In fact, I'll tell you something later. So you see, if T cannot, so T cannot have, because if T had 3 no cut vertices, right, their removal does not disconnect the graph, right? Removing V, so T minus V is connected, right? T if T minus W is connected, if T minus Z is connected, then obviously G minus V will also be connected, right? G is a much bigger thing. Do you guys agree with this? I mean, G is a better thing, right? If G has 2 no-cut vertices, then how can T have more than 2 no-cut vertices? Is it okay with everyone? Yeah, because you can see if T has like 3 of them, right? Or let's just say if T has 1, if T has any no-cut vertex, right? If V is a no-cut vertex for T, then V is also a no-cut vertex for G, right? Because you can just see this, if T minus V is connected, then G is a superset. Right? G has more edges, right? Then obviously it will also be connected. Between any 2 points in G, there is a path in T which does not use V. So that path will also be there in G, obviously, right? Okay, take a minute. Then the proof is done. Yeah. VWZ is not G. VWZ are, okay, let me say it. Yeah. VWZ are, let's say if T has more than 2 no-cut vertices, just for the sake of contradiction. These are the no-cut vertices, right? So, right. See, but it's very simple if you think about it like this. See, if G has exactly 2 no-cut vertices, so G has 2 vertices whose removal does not disconnect the graph, right? Then is it possible that T will have more than 2 such things? No, right? Because if V is no cut for T, what does it mean? It means that removal of V is connected. If T minus V is connected, then G minus V is obviously connected. Right? Because G has more edges. Any edge, not more, not just more, but anything that is there in T is also there in G, right? Right. So if T minus V is connected, meaning that in T minus V, if you have 2 points x naught, y naught, then there is a path. Then this path will be there in G also. G has more things, right? So it means that T has only 2 no-cut vertices. T cannot have less than 2 no-cut vertices. Every tree has at least 2 no-cut vertices, right? So T has exactly 2 no-cut vertices. Okay, let's see. Hold on. But I think we have messed up a little bit. Let's see. So T has exactly 2 no-cut vertices, right? So that implies that T is a path. Okay. No, but how do, our job was to show that G is a path. But it is not that difficult. Now, Chandan had made a point about what if there is a path joining all the vertices. We are down to that situation now. I mean, the proof is now very simple, right? Because see, G has exactly 2 no-cut vertices. Okay, we assume that. That means that its underlying tree. Now remember, the underlying tree uses all the vertices, right? T has all the vertices of G. T doesn't have all the edges. So the underlying tree is just a path. The underlying tree is just a path. What does it say about G? It means that G may, there are no other vertices outside. No, there's nothing else in G. There are no vertices in G which is outside this. Does everybody agree with that? Right? Now the job is much simple. Right? So in the tree, that's right. That's right. Because the tree uses all the vertices. That is a good thing, right? Tree is a connected graph, is a connected subgraph of G, but it is like it uses up all the vertices also. So it is on the boundary. It's a maximal among all. That's why it's called a spanning tree. The word spanning is, that's what it means here. So it means that G cannot have anything outside, but now the job is much simpler. Now what can G try to, what tricks can G try to pull up? G can have some edges like this, right? Those are the only things that G can do now. Is that right? Those extra things that G can have. The red ones are for the tree, right? This extra things the G can have, but you can see it cannot have those also. I mean, if it has those things, then it creates a cycle, and then some vertex, this becomes again no cut. Right, but now it's very simple. So what Raghav was saying earlier, cycle, it's about cycles only in the end. But now we can do the reasoning because there is only simple cycle. There is no thing outside the cycle. It's not a cyclic system now, it's just a cycle. Okay, so if G has some extra edges, now G can only have extra edges. G cannot have extra vertices. No, only extra edges. Now what can it do with these extra edges? It can only create these cycles. But if it creates these cycles, then this becomes no cut. Two already no cut are there, but this also becomes no cut, but that's a contradiction. But that was bound to happen, right? So the problem becomes much simpler if you use a tree. A tree is a basis for the graph, just like the 3 unit vectors you use, right, to write every vector. I mean, in some level, they are very similar. Yeah. Yeah. I mean, the fact that every tree has exactly n-1 edges, and if you take a 3-dimensional space, that there are 3 vectors, different directions, and you cannot do it less than 3. Those are the similar statements. The same proof applies. But the point is, yes, trees are like the basis. So come down to a tree and do the reasoning, and you see how easy it becomes. Okay. So what have we proved? We have proved that we have basically given a new definition for paths, right? So a graph with a connected graph, obviously, exactly 2 no cut vertices is a path, right? And obviously a path also has exactly no 2 cut vertices, right? Is a path. Okay. So this means you have a new definition of path, right? Path means same thing as exact. So now this is a new def. So initially we started with some very simple definition, but this is the different definition. It's kind of a definition now, right? Because you could take it as a definition, right? Because these are the only things that paths are the only things that satisfy this. Exactly 2 no cut vertices. Obviously, now this is not a definition that we should go around quoting, in the sense that this is it's a property, but it's a characterizing property. Okay. But this is a very good definition of a path, because this kind of defines, now this is very interesting, because this is interesting because now see, why are trees interesting? Because trees are the solution of a minimization problem, right? Trees are the solution of a minimization problem, like graph. So given a graph, or given a graph, find a minimum graph with minimum number of edges which is connected. Answer is that's the problem. Answer is tree. So tree is useful because it's the solution of a minimization problem. Okay. Similarly, now we have actually defined a path as a solution of a minimization problem. What? A path is a graph with minimum number of no-cut vertices, because every graph has at least 2, we know. Yeah. So this can be is sort of like a universal definition of a path. Defining something as the minimum of something, of some property, Okay, a path is a graph with minimum number of, so it's like you have the set of all the graphs and you have asked a minimization question and the output is path, family of all paths. Okay, so we have ended up defining paths in a very special way. Okay, so this is the definition of a path as minimum of something. Now I'm writing apparently the same thing again for a reason. You see, just trying to abstract it one at a time. Okay, I've removed this. This is not the important point now. The importance is that we have defined something as the minimization as the minimum of some problem. Okay. Why is this? Why are these kind of definitions very nice? Because suppose if O is an object, okay, and let's say that it has a property. O has a property that now this could be a path, it could be something else, collection of vectors, or you know, an equilateral triangle. O is minimum of some question of something. So O has this property. Other things may also have this property, maybe to start with, but minimum is unique, right? So this means that this property can be actually used to define O. That implies that this property defines O. So you actually get a definition of O. But this may be a much more neater definition. Like O may be a very complicated thing, right? You construct it out of several things and several lines, points, or whatever, some distance, some other complicated thing. But if you can show that this very complicated thing, which you just cannot understand at one go, if you can show that it is a minimization of some question, then boom, you have a different definition, which is, O, that you can say that O is not that complicated thing, but O is an object which has minimum area among all something. So you get a much simpler definition by that. And this is a way in which higher maths, what is called category theory, universal properties work. So we find a property of something which is saying that it is a minimum of something, some kind of property. But then that property is of a nature that it ends up actually defining the object. Okay, and this is the kind of thing that's happening here. Trees, we had such a simple property that it's a minimum of something, right? Okay, so we have done this problem, and so now we can obviously stop. We should stop, right? Yeah, I wanted to do many other things, which what happens when you remove vertices from a tree. Okay, you get many different trees, and so wanted to study some relations there, and that's used in a lot of problems, but we will do it next time. Okay, yeah. So are there any questions? We have done a very nice proof of this thing today, right? That a graph with exactly no two cut vertices is the path. Because usually, when I was studying, I'm still studying in the sense that, yeah, this thing, then we had a problem. We had this exact problem in something. I gave a very bad proof, very long proof. Okay, I discussed with many people. Then I got up in the end, also wrote a very big long proof. But today we got a very nice proof. Maybe I can show that proof. I had written it at some point. I'll just 1 second if I can find it. Meanwhile, just see if you guys have any questions. I had actually written it also. By that time, I didn't have this intuition that you should go with the minimum thing and so on, with the tree and so on. Anyways, it takes a long time. Anyways, so are there any questions? No questions? Okay. Okay, then I think, yeah, we can stop. We will not have any class tomorrow, maybe Friday or Saturday.